Welcome to my channel, where we drift gently through the cosmic deep, exploring the grandest stories the universe has to tell. Tonight, we're embarking on a slow, soothing journey through one of the most spectacular and surprisingly gentle phenomena in all of space: galactic tides and the majestic dance of colliding galaxies. Now, before we float off into the star-filled darkness together, I'd love to know where in the world you're watching from and what time it is for you right now. Are you settling in for the night in Stockholm? Or perhaps it's a quiet afternoon in Melbourne? Drop a comment below and let me know. There's something wonderfully comforting about knowing this little community of cosmic dreamers is scattered across time zones, all gathered here to ponder the same beautiful mysteries. If you find these gentle journeys through science helpful for unwinding or simply satisfying your curiosity, please consider giving this video a like and subscribing to the channel. It helps more fellow stargazers find their way here, and it means the world to me. I should mention that while I'll do my best to keep things soothing and not too riveting, there's always the small risk that you might find yourself wide awake at midnight, thinking about spiral arms and stellar nurseries. But if that happens, well, at least you'll have learned something extraordinary about the universe we call home. So settle in, let your shoulders drop, and take a long, slow breath. Tonight, we're going to discover how galaxies, those island universes containing hundreds of billions of stars, can dance together in slow-motion ballets that unfold over millions of centuries. These aren't the violent crashes you might imagine, but rather elegant gravitational waltzes that create some of the most beautiful structures in the cosmos. When we look up at the night sky, the stars appear fixed and eternal, like tiny diamonds scattered across black velvet. But if we could speed up time by millions and millions of years, we'd witness something extraordinary. Entire galaxies moving through space, approaching each other across the cosmic void, and beginning an intricate gravitational dance that reshapes both participants in the most remarkable ways. You see, galaxies aren't solitary wanderers drifting alone through the universe. They're social creatures, gravitationally bound together in groups and clusters, constantly influencing each other across vast distances. And occasionally, two of these magnificent spiral cities of stars will find themselves on a collision course, beginning one of nature's most spectacular performances. But here's the beautiful paradox. When astronomers say galactic collision, they don't mean the catastrophic smashing together that the word collision might suggest. Instead, picture two vast clouds of fireflies approaching each other in the darkness. The fireflies might swirl and intermingle, creating new patterns and structures, but they rarely collide directly with one another. This is much closer to what happens when galaxies interact. The secret lies in something called galactic tides, invisible gravitational forces that become the choreographers of this cosmic ballet. Just as our moon's gravity creates tides in Earth's oceans, pulling water toward it in a gentle bulge, the immense gravitational field of a galaxy creates tides in any nearby galactic neighbor. These tidal forces don't pull uniformly. Instead, they create a differential pull that's stronger on the near side of a galaxy and weaker on the far side. Imagine you're gently stretching a piece of soft clay. The part closest to your hands experiences more force than the part farther away. This is exactly what happens when two galaxies approach each other. The differential gravitational pull begins to stretch and distort their graceful spiral structures, pulling out long streamers of stars, gas, and dust that can extend for hundreds of thousands of light years into the space between galaxies. These extended ribbons of stellar material are called tidal tails, and they're among the most photogenic features in all of astronomy. Picture delicate fingers of starlight reaching across the darkness, like cosmic auroras painted in blue and gold. The Hubble Space Telescope has captured countless images of these ethereal structures, showing us galaxies that look like jellyfish trailing luminous tentacles through the cosmic deep. But tidal tails are more than just beautiful. They're stellar nurseries in disguise. Recent observations have revealed something quite extraordinary. These stretched-out streams of material are absolutely teeming with newborn stars. As the gravitational forces compress and jostle clouds of hydrogen gas within the tails, they trigger spectacular episodes of star formation, creating what astronomers poetically call strings of pearls. brilliant clusters of young stars strung out along the tidal streams like jewels on a cosmic necklace. Each of these stellar pearls contains roughly 1 million brand new stars, all born in the turbulent environment of the galactic interaction. These baby stars are incredibly young by cosmic standards, only about 10 million years old, which means they formed well after the galactic collision began. They're the children of chaos, born from the gravitational turmoil that occurs when galaxy meets galaxy. What's particularly fascinating is that these stellar nurseries seem to form at roughly the same rate all along the tidal tails, creating evenly spaced clusters that stretch for thousands of light years. It's as if the universe has its own sense of rhythm and timing, orchestrating stellar birth in perfect intervals along these cosmic highways. The process that creates these stellar pearls begins when previously quiet clouds of molecular hydrogen get caught up in the gravitational tug-of-war between the two interacting galaxies. Before the encounter, these gas clouds might have remained dormant for billions of years, too sparse and cool to collapse and form stars. But the collision changes everything. The clouds get jostled and compressed, bumped into each other like cosmic bumper cars, until the hydrogen reaches a critical density. Once that threshold is crossed, gravity takes over, and the gas begins its inexorable collapse towards stellar birth. This process was likely even more common in the early universe, when galaxies were younger, smaller, and more frequently encountered each other. The cosmos was a more crowded place billions of years ago, with galactic collisions happening much more often than they do today. Those ancient interactions may have been responsible for creating many of the globular star clusters we see orbiting galaxies today, ancient stellar cities that have survived for most of cosmic history. As we drift through this story of galactic encounters, it's worth pausing to appreciate the incredible scales involved. When we talk about galactic collisions, we're describing events that unfold over hundreds of millions, sometimes billions of years. The tidal tails we see in telescopic images represent gravitational sculptures that have been slowly forming for longer than complex life has existed on Earth. The stars being born in these interactions will shine for trillions of years, long after our own sun has exhausted its nuclear fuel and faded to a dim white dwarf. And yet, despite these almost incomprehensible timescales, the physics governing these interactions is surprisingly familiar. The same gravitational forces that cause ocean tides on Earth, that keep our moon in orbit, and that make apples fall from trees, are responsible for reshaping entire galaxies. It's a beautiful reminder that the universe operates according to the same fundamental laws at every scale, from the quantum realm to the cosmic web. Tonight, as you drift off to sleep, perhaps you'll dream of those stellar pearls strung along their tidal highways, newborn stars twinkling in the cosmic darkness like distant campfires. And maybe you'll smile knowing that somewhere in the universe, galaxies are dancing their slow-motion waltz, creating beauty on a scale almost too grand to imagine, all guided by the gentle pull of gravity's invisible hand. The fate of these newborn stellar clusters remains one of astronomy's most intriguing mysteries. Some may survive as gravitationally bound families for billions of years, eventually becoming the globular clusters that orbit like distant satellites around their host galaxies. Others might disperse, their constituent stars wandering off to join the diffuse stellar halo that surrounds most large galaxies like a faint, spherical aurora. And some clusters may be ejected entirely, cast out into the lonely darkness of intergalactic space to become orphaned communities of stars, forever separated from their galactic homes. This uncertainty adds a poetic melancholy to the story. These stellar nurseries, born from cosmic chaos, face an uncertain future. They're like messages in bottles cast into the ocean of space, and we can only wonder where the currents of gravity will carry them over the eons to come. Now, let's turn our attention to a collision that strikes much closer to home, both literally and figuratively. Our own Milky Way galaxy is destined for its own cosmic encounter, approaching what astronomers have long called the inevitable collision with our nearest large neighbour, the Andromeda galaxy. For over a century, we've known that Andromeda was racing toward us through the darkness at approximately 68 miles per second. That might sound terrifyingly fast until you realize that at cosmic scales, this is actually quite a leisurely pace. But here's where the story takes a fascinating turn. Recent research has thrown our understanding of this future collision into delightful uncertainty. Using data from the Gaia spacecraft and the Hubble Space Telescope, astronomers have discovered that the gravitational influences of other galaxies in our local group, particularly the Large Magellanic Cloud and the Triangulum Galaxy, play a much larger role than previously thought. These additional gravitational players act like cosmic referees, subtly altering the orbital dance between Andromeda and the Milky Way. The result? What was once considered an inevitable collision in approximately 4.5 billion years is now viewed as only a 50-50 probability. In roughly half of computer simulations, the two galaxies perform an elegant cosmic pas de deux, sweeping past each other at a distance of about 500,000 light-years before retreating into the darkness, only to return for another encounter in the distant future. This revision in our understanding demonstrates something beautifully humbling about astronomy. Even our most confident predictions about cosmic events can be overturned by new data and more sophisticated modeling. The universe, it seems, always has a few surprises tucked away in its vast sleeves. Should the collision eventually occur, the transformation would be extraordinary. Computer simulations show that the merger would unfold over several billion years, with multiple close approaches before the two galaxies finally settle into their gravitational embrace. The end result would likely be a single massive elliptical galaxy, a cosmic metropolis containing well over 1 trillion stars. But here's the remarkable thing. Despite this galaxy-spanning catastrophe, the chances of any two individual stars actually colliding would be essentially zero. Space is so vast and stars so relatively tiny that even during a galactic merger, they pass by each other like ships in the cosmic night. To put this in perspective, if our sun were the size of a ping-pong ball, the nearest star would be a pea located over 1,000 miles away. Even in the densest regions of colliding galaxies, stars maintain their splendid isolation. The real drama would occur on larger scales. The supermassive black holes lurking at the centers of both galaxies would begin their own gravitational waltz, spiraling ever closer over millions of years until they finally merged in a crescendo of gravitational waves that would ripple through the fabric of space-time itself. This cosmic collision would create some of the most powerful gravitational wave signals in the universe, though occurring on timescales far too long for our current detectors to observe directly. Meanwhile, vast quantities of gas and dust would be stirred up during the merger, potentially fueling spectacular bursts of star formation, and perhaps even triggering the birth of a quasar as material spirals into the newly combined supermassive black hole. The night sky, if Earth somehow survived this cosmic transformation, would be painted with the light of billions of newborn stars. For a more immediate glimpse into our cosmic future, we can look to the Antennae galaxies, a pair of spiral galaxies located about 70 million light-years from Earth. These two cosmic dancers began their gravitational embrace several 100 million years ago, and are currently in the midst of a spectacular stellar baby boom. The collision has triggered one of the most intense episodes of star formation ever observed, with billions of new stars being born in massive clusters scattered throughout both galaxies. The Antennae showcase the full life cycle of galactic interaction beautifully. About 1.2 billion years ago, they were two separate peaceful spiral galaxies, much like our Milky Way and Andromeda today. As they approached each other, their first close encounter occurred roughly 600 million years ago, creating the long, graceful tidal tails that give the system its distinctive appearance. Now, in their second or third pass, they're experiencing the peak of their stellar birth phase, with new stars forming at a rate hundreds of times faster than in isolated galaxies. The system is dotted with brilliant blue star-forming regions, like cosmic fireworks frozen in time. Many of these stellar nurseries are so massive and densely packed that they're creating some of the most extreme stellar environments found anywhere in the local universe. These superstar clusters contain millions of individual stars crammed into regions only a few light-years across, creating stellar densities that would make our sun's neighborhood seem almost empty by comparison. But most of these stellar cities won't survive. astronomers estimate that only about 10% of the newly formed clusters will remain gravitationally bound beyond their first 10 million years. The vast majority will gradually disperse, their constituent stars becoming part of the smooth background glow of the merged galaxy. However, the most massive clusters, perhaps 100 or so, may survive to become the globular clusters of the future, ancient stellar communities that will orbit the merged galaxy for billions of years to come. As we contemplate these cosmic collisions, there's something deeply poetic about their timescales and outcomes. These are stories that unfold over periods longer than life has existed on Earth, yet they follow the same fundamental physical laws that govern falling leaves and ocean tides. They remind us that we're part of something vast and ongoing, a universe in constant, slow-motion transformation. The Antennae galaxies also reveal something rather extraordinary about the diversity of galactic collisions. Not every cosmic encounter follows the same script. The geometry of the approach, the relative masses of the participants, their gas content, and even their orbital velocities all combine to create unique outcomes. Some collisions are gentle grazing encounters that barely disturb the participants' spiral structures. Others are nearly head-on impacts that completely transform both galaxies into something entirely new. One of the most spectacular examples of this diversity can be found in ring galaxies, cosmic rarities that form under very specific circumstances. When a compact galaxy plunges almost perpendicularly through the disk of a larger spiral galaxy, it creates something that looks like a cosmic bullseye. The most famous of these is the Cartwheel galaxy, located 500 million light-years away in the constellation Sculptor. Picture dropping a stone into a perfectly still pond. The ripples spread outward in expanding circles, carrying energy away from the point of impact. The Cartwheel galaxy represents something remarkably similar, but instead of water waves, we're witnessing a density wave of star formation propagating through a galactic disk at nearly 200,000 miles per hour. The collision occurred roughly 400 million years ago when a smaller intruder galaxy, possibly one of the compact objects visible near the ring today, careened through the Cartwheel's core. The impact sent a gravitational shockwave rippling outward through the galaxy's spiral arms, compressing gas clouds and triggering an ongoing fireworks display of stellar birth that continues to expand even today. What makes the Cartwheel particularly fascinating is its dual ring structure. There's a bright inner ring where the initial shockwave compressed the densest regions of gas, and a larger, more colourful outer ring that's currently dominated by active star formation and supernovae. This outer ring, which has been expanding for about 440 million years, is so large that our entire Milky Way galaxy could fit comfortably inside it. The ring isn't perfectly uniform either. Hubble's detailed observations reveal that it's dotted with brilliant blue knots, each one a gigantic cluster of newborn stars, and immense loops and bubbles blown into space by exploding stars going off like a string of cosmic firecrackers. The expanding ring acts like a snowplow, pushing through the galaxy's interstellar medium and triggering starbirth wherever it encounters dense pockets of gas and dust. But perhaps the most remarkable aspect of the Cartwheel is its transitional nature. This isn't a permanent transformation. The galaxy is slowly recovering its original spiral structure, with faint arms or spokes beginning to emerge between the outer ring and the central nucleus. It's like watching a flower bloom in extreme slow motion, as the galaxy gradually heals from its cosmic wound, while the expanding rings continue their outward journey. These ring galaxies offer us a unique window into the physics of density waves and shock propagation in galactic disks. Computer simulations show that the ring expansion is remarkably regular and predictable, maintaining its integrity as it sweeps through the galactic medium. The process reveals how efficiently energy from a collision can be transported across vast distances, creating organized structures from what initially appears to be chaotic disruption. The Cartwheel also demonstrates something profound about galactic resilience. While the collision has dramatically altered the galaxy's appearance, recent spectroscopic studies reveal that large portions of the system remain relatively unaffected by the impact. The collision primarily influenced the outer regions where the density wave passed through, while the inner galactic structure retained many characteristics of a typical spiral galaxy. This suggests that galaxies are more robust than we might expect, capable of maintaining their essential nature even while undergoing dramatic transformations. As we drift deeper into this story of cosmic encounters, it's worth pausing to consider the role of dark matter in these galactic ballets. While we can't see dark matter directly, it makes up roughly 85% of all matter in the universe, and it plays a crucial but invisible role in galactic collisions. Each galaxy is embedded within a vast halo of dark matter that extends far beyond the visible stars and gas. These dark matter halos interact gravitationally during collisions, creating complex dynamics that influence how the visible components behave. The dark matter doesn't collide in the traditional sense, because dark matter particles interact only weakly with each other and with ordinary matter. Instead, the dark matter halos pass through each other like ghostly shadows, but their gravitational influence continues to shape the merger long after the visible components have begun their dance. This creates a fascinating separation between the dark and ordinary matter during some collisions, with the dark matter leading the way while the gas and stars lag behind, slowed by their interactions with each other. Computer simulations that include dark matter reveal merger dynamics that are far more complex and beautiful than those involving ordinary matter alone. The dark matter halos can oscillate around each other multiple times before finally settling into equilibrium, creating gravitational disturbances that continue to influence star formation and galactic structure for billions of years after the initial encounter. One of the most intriguing aspects of galactic collisions is how they can trigger the formation of some of the universe's most extreme objects. During major mergers, vast quantities of gas and dust get funneled toward the galactic centers, where supermassive black holes lurk in patient darkness. This sudden influx of material can awaken these gravitational giants, transforming them from quiet observers into active galactic nuclei that outshine entire galaxies. The process begins when the collision disrupts the orderly rotation of gas within each galaxy. Normally, this gas orbits stably around the galactic center, like water circling a drain but never quite falling in. But the gravitational chaos of a merger can rob this gas of its angular momentum, sending it spiraling inward toward the central black hole. As the material falls inward, it forms an accretion disk, heating up to millions of degrees and beginning to glow with the light of 1,000 billion suns. The result can be a quasar, one of the most luminous objects in the universe, visible across billions of light-years of space. These cosmic lighthouses may have been much more common in the early universe when galactic collisions occurred more frequently. Today, we see them primarily as distant beacons from cosmic antiquity, fossil light from an era when the universe was younger and more violent. But not all encounters between supermassive black holes end in such spectacular fashion. When two galaxies merge, their central black holes begin a complex gravitational dance that can last for millions of years. Initially separated by thousands of light-years, they spiral slowly inward, their orbital energy gradually dissipated through interactions with nearby stars and gas clouds. This process, called dynamical friction, acts like cosmic brakes, causing the black holes to lose energy and spiral ever closer together. Eventually, when they reach separations of only a few light-years, gravitational wave radiation takes over, causing the final death spiral to accelerate dramatically. In the last few minutes before merger, the two black holes complete thousands of orbits, whipping around each other at significant fractions of the speed of light, before finally coalescing in a burst of gravitational waves that ripples through the fabric of spacetime itself. These gravitational wave chirps represent some of the most powerful events in the universe, releasing more energy in their final moments than all the stars in the observable universe combined. Yet they do so almost silently, disturbing space and time, but producing no light, no heat, no electromagnetic radiation of any kind. They're cosmic whispers that we've only recently learned to hear, thanks to instruments like LIGO and Virgo that can detect distortions in spacetime smaller than 1,000th the width of a proton. The merger of supermassive black holes also represents a kind of cosmic archaeology. Each black hole carries with it the history of its host galaxy, the accumulated mass of billions of years of stellar evolution and galactic growth. When they merge, they create a single object that contains the gravitational memory of both galaxies, a dense archive of cosmic history compressed into a region smaller than our solar system. As we contemplate these vast scales of space and time, these billion-year dances of matter and energy, there's something wonderfully humbling about our perspective as observers. We're fleeting creatures on a small rocky planet, yet we've learned to read the cosmic stories written in starlight and gravitational waves. We can trace the histories of galactic encounters that began before our solar system formed and will continue long after our sun has faded to a cold ember. And perhaps most remarkably, we've discovered that these seemingly violent cosmic collisions are actually agents of creation rather than destruction. They trigger the formation of new stars, sculpt beautiful structures from gravitational chaos, and help distribute the chemical elements necessary for life throughout the universe. In a very real sense, galactic collisions are part of the cosmic evolutionary process that made our existence possible. The heavy elements in our bodies, the oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged in the nuclear furnaces of stars. Many of those stars were born in the turbulent environments of galactic interactions, their formation triggered by the same gravitational forces that create tidal tails and stellar pearl strings. We are, quite literally, children of cosmic collisions, made from stardust scattered by ancient galactic encounters. As you settle deeper into the gentle embrace of sleep tonight, perhaps you'll dream of galaxies dancing their slow waltz across the cosmic ballroom, their spiral arms trailing streams of newborn stars like luminous scarves in the stellar wind. And maybe you'll smile knowing that, even in the vast loneliness of space, galaxies find each other, drawn together by the patient pull of gravity, creating beauty from chaos and new beginnings from apparent endings. These cosmic encounters remind us that the universe is not a static museum of distant lights, but a dynamic, ever-changing theatre where the grandest stories unfold over timescales that dwarf human history. Every galaxy we see through our telescopes is part of this ongoing narrative, shaped by ancient collisions and preparing for future encounters in the endless dance of cosmic evolution. The story of galactic collisions becomes even more intimate when we consider the Mice galaxies, another spectacular pair caught in their gravitational embrace about 300 million light-years from Earth. Named for their distinctive long tails that stretch behind them like cosmic whiskers, these two spiral galaxies offer us a different chapter in the grand narrative of galactic encounters. What makes the Mice particularly fascinating is their asymmetry. While both galaxies sport elongated tidal tails, one stretches much farther than the other, creating an almost whimsical appearance that astronomers couldn't resist naming after those small creatures that scurry through our earthly homes. This lopsided structure tells us something important about the physics of galactic interactions. The outcome depends not just on the masses of the participants, but on their internal structure, gas content, and the precise geometry of their approach. The longer tail appears to have been drawn from the smaller of the two galaxies, its outer regions more easily stripped away by the gravitational influence of its larger companion. As these stellar streams extend into space, they carry with them not just individual stars, but entire stellar associations and the raw materials for future generations of cosmic citizens. Some of these wayward stars may eventually find new homes in the merged galaxy's extended halo, while others might drift away entirely, becoming part of the sparse population of intergalactic wanderers. But perhaps the most poetic aspect of the Mice is how they demonstrate the reversible nature of gravitational encounters. Computer simulations suggest that these galaxies have already completed one close passage and are now approaching their second rendezvous. Like cosmic dancers who separate briefly before coming together again, they're performing a multi-act ballet that will eventually culminate in their permanent union billions of years from now. This back-and-forth motion reveals something beautiful about the nature of gravity itself. Unlike other forces we encounter in daily life, gravity never truly lets go. No matter how far apart two objects become, they continue to influence each other across the void, their mutual attraction growing weaker with distance but never disappearing entirely. In the case of the mice, this means their story was written billions of years ago when they first began to feel each other's gravitational whisper across the darkness. The extended timescales of these cosmic courtships allow for multiple episodes of enhanced activity. Each close approach stirs up the galaxy's interstellar medium, compresses gas clouds, and triggers new waves of star formation. The mice are currently experiencing one such burst of stellar birth, with brilliant blue knots of newly formed stars scattered throughout both systems like sapphires caught in spiderwebs of dust and gas. These periodic episodes of rejuvenation may explain why some galaxies appear much younger than their actual age. A galaxy that underwent a major collision or merger in its recent past might still be glowing with the light of stars formed during that encounter, making it appear more vibrant and active than an isolated galaxy of similar vintage. It's cosmic plastic surgery of a sort, where gravitational interactions can restore a galaxy's youthful appearance long after its original stellar population has begun to age. As we drift further through the catalogue of cosmic encounters, we encounter objects that push the boundaries of what we might consider normal galactic behavior. Take, for instance, the spectacular system known as Stephan's Quintet, a visual grouping of 5 galaxies that appears to be engaged in a complex gravitational dance. Though one of the galaxies is actually much closer to us than the others and only appears associated by chance, the remaining 4 are indeed interacting in ways that create some of the most dramatic shockwaves ever observed in intergalactic space. These shockwaves, visible as glowing filaments of heated gas, reveal the invisible collision between galaxies and the thin material that fills the space between them. As galaxies move through their local environment, they create bow shocks in the surrounding medium, much like a boat creates a wake as it moves through water. But in Stephan's Quintet, the interactions are so violent that they're stripping away entire clouds of gas and heating them to temperatures of millions of degrees. The system showcases another fascinating aspect of galactic evolution: the role of galaxy groups and clusters in shaping individual members. Galaxies don't exist in isolation but are embedded within larger structures that can profoundly influence their development. In dense environments like galaxy clusters, interactions become more frequent and complex, with multiple participants joining the gravitational dance simultaneously. These crowded cosmic neighborhoods can accelerate evolution in remarkable ways. Galaxies may undergo multiple encounters over relatively short periods, each interaction adding its own chapter to the story. Some galaxies in these environments become so thoroughly processed by repeated encounters that they're transformed into entirely different types of objects, stripped of their spiral structure and gas content to become smooth, elliptical systems dominated by older stellar populations. But perhaps nowhere is the drama of galactic interaction more visible than in the phenomenon of galactic cannibalism, where larger galaxies gradually consume their smaller companions over billions of years. This process, more properly called galactic accretion, is happening in our own cosmic neighborhood, as the Milky Way slowly absorbs several smaller satellite galaxies. And so our gentle journey through the cosmic deep draws to a close, leaving us floating peacefully among the stellar streams and tidal whispers of galactic encounters. We've witnessed the universe's grandest choreography, where islands of stars dance their billion-year waltzes across the darkness, creating beauty from chaos and new beginnings from ancient endings. Sleep well, dear cosmic wanderer, and may your dreams be filled with the soft glow of stellar nurseries and the patient pull of gravity's invisible hand, forever shaping the heavens above.